Okay, Meow. Today we're going to talk about limits. It's one of the first ideas of calculus. The easiest way to explain what a limit is basically what is a function doing as we approach some value for x. And a really nice way to see that is with a graph. So we're basically asking ourselves, what is the graph doing as we approach some value of x? It might be 1, 2, 5, could be infinity. That's what we're going for. Okay, Meow, so go ahead and pause the video, draw in this graph really quick, and then unpause it here in a second. Okay, Meow, so I think I gave you enough time. Let's go ahead and just try some. They're really not that bad with a graph. They're not hard at all, really. So the notation here, this says the limit as x approaches, wrong one. This is what I'm looking for. The limit as x approaches 0 of f of x, okay? This is always just gonna say limit. This is your x value that you're approaching. Sometimes it'll say f of x, sometimes it'll actually have the function written out. So this says, what is the graph doing as we get close to with the x value of 0? So find your x value, go up to your graph, and we basically just want to know, what is this approaching? Okay, so if you come in from the left side, it is approaching 1, 2, 3, 4. If you're coming in from the right side, it is approaching 4. So that limit is 4. Pretty easy. Okay, next one says the limit as x approaches 1. So we find 1, the limit as x approaches 1, it looks like it's approaching this point, coming from the left, coming from the right. They both agree. It's going to be 3. All right, next one. The limit as x approaches 3. 1, 2, 3. So on this one, it kind of looks weird because we have an open circle, and then it's actually defined down here. The open circle has nothing really, it doesn't affect the limit at all on this one, because if you look, coming in from the left, it is approaching 2. Coming in from the right is approaching 2. Okay, so the limit here is actually 2. That would be your answer. All right. On this, that's just discontinuous is what we would say. And if we had more time in the year, we would actually go into continuity and we would say this one is not continuous. This function is not continuous. The easiest way to describe if something is continuous, can you trace it with your pencil without actually picking it up? Well, here we can't because we have to pick it up and go to here. This is actually called a removable discontinuity. Okay, if you're taking calc next year, that's probably something to try to remember. That's a removable discontinuity. Okay, these are all called two-sided limits, the ones that we have done, because we're doing the limit as we go from the left and the right, and they both agree. That's a two-sided limit. Okay, Meow, the one that I actually started with, I actually want to look at it now. This is a one-sided limit. You can tell it's a one-sided limit because there's a little sign right here. All right, so what this actually says, it's a limit as x approaches 4, and that says from the left. So as we come in from to 4 from the left, 1, 2, 3, 4. So I'm looking here. I want to be from the left. So I'm actually, this is the one that I'm looking at. So basically 3.9, 3.99, 3.999, those are the values that I'm looking at. So it's going to be this part of the graph. As we come in from the left, it looks like it is approaching 4. Okay, Meow. So the next one says the limit as x approaches 4 from the right. All right, so you're looking at your graph, you're coming in from the right on this one. So it's going to be this way. 4 from the right. 4 from the right would be 1. Okay, this is another discontinuity. All right, this one is called a non-removable discontinuity. It's also called a jump discontinuity. You can tell it's a jump because you are jumping to get to the next part of the graph. Okay, that's another thing if you're taking it next year, try to remember that. Okay, now if we look at the two-sided limit, well, in the two-sided limit, which one do you think is going to be? Is it going to be 4 or is it going to be 1? Actually, on this one, does not exist. Because in order for a two-sided limit to exist, the one-sided limits have to actually agree. Okay. One more. It says the limit as x approaches infinity. So this would probably help if we could see a little bit more of the graph. So as we go to infinity, that's what this is saying. As x goes to infinity, what is the graph doing? Well, if you remember back to Algebra 2, earlier part of the year, you see this little dashed line. That tells you that that's an asymptote, and that's what that's actually approaching. So as x approaches infinity, our graph looks like it's approaching 2. All right. Limits and asymptotes, you'll see them kind of going together a lot when you get into calc. All right, now, so we've done the graphs. Those hopefully weren't too bad. Now let's try an actual function. So let's try this one. The limit as x approaches 5 of x squared. Now what we could do is we could graph y equals x squared and then see where's the limit telling us, like what's the left-sided limit and right-sided limit kind of approaching. The easiest way though is to actually do this algebraically. The first thing you always want to try with a limit is to just plug in the value. So the limit as x approaches 5, just plug in a 5 there. 5 squared is 25. If you get an actual number and you know that this is continuous, that's going to be your answer. Now, if this wasn't continuous, if you had something where you knew that it would go like this and then like this, if it was some piecewise function or something like that, then you'd have to be a little bit more careful. But we know this is continuous. It's got to be 25. Okay, meow. Next one. You've probably heard me say meow quite a bit. That's actually going to be your watch code. You have to tell me how many times have I said meow. You might want to, I don't know, pause the video, go back, start counting. I'll give you a second. Okay, so hopefully you counted all of the meows. I'm now up to 11, I think, if I counted right. This next one, the limit as x approaches pi over 6. So the first thing we always want to try, plug it in. Sine of pi over 6. Hopefully you have not forgotten your trig values. Sine of pi over 6 is a half. All right, a couple more. This one, you should be able to do it by yourself. Just plug in a 2. You got 8 plus 8, 16. No problem. Last one. Go ahead and try it. Okay, so when you tried it, you probably got 0 on top and 0 on the bottom. And this is where you would probably get frustrated because 0 over 0, some people say, well, that's 0. Some people say, well, that is undefined. Other people would say it's infinity. And the truth is, that's something that we don't know. It depends. You have to figure it out. This is called the indeterminate form because sometimes that's going to be a number, sometimes it's going to be 0, sometimes it's going to be undefined. We don't actually know. You have to actually do a little bit of work. So one of the first methods of solving something when you have an indeterminate form is to actually just factor this. And then when you factor it, some things would cancel out. So the one thing you have to make sure you're careful with is when you're showing your work, this limit part cannot go away. You always have to carry that down. So we're going to factor this. These are going to cancel each other out. when you write down your next step, that limit still needs to be there. The reason why is because if you go straight from this and just write this is equal to x plus 3, well, it really isn't, because the graph of this looks different than the graph of just x plus 3. It's a little ticky-tacky thing, but it's kind of important. So once we simplify it down, now we want to try to plug it in. And hopefully when you plug it in the second time, it actually will work and you get a number. This one's going to be 6. All right. You could actually graph this if you wanted to. Like if you remember back to Algebra 2 when we graph these types of functions, if you remember what happens when stuff cancels out is it actually creates a hole. So this graph, it's basically the graph of x plus 3, but you have a hole right here. So if you look at your limit, coming in from the left, it's approaching 6. Coming in from the right, it approaches 6. That's perfectly fine that there's a hole there. The limit still exists. Like they're still both approaching the same value. So that limit is still there. All right, Mel. That's it for today. I should be emailing you out some problems to try, so check your email. And then don't forget to email me how many times I've actually said meow. It's a lucky number. Until next time.